Hi guys, in this video we're going to develop a functionality that allows a terrain material to procedurally wet itself. The approach you're going to see in this video takes inspiration from how Naughty Dog developed the same system for the Uncharted series. To efficiently follow this video, make sure to have clear in your mind the concept I explained in my previous videos about texture transitions and height blending. Very often, to give life to the worlds we're building, we'll find ourselves having to implement static or dynamic weather functions for our shaders. In this video, we'll discuss how to approach such problem on a terrain material. As said, this weather function can be either static or dynamic. In the first case, we could simply realize a separate wet version for our environment and eventually work on the rules that handle the switch between the two versions of the same scene. In the second case, the approach we decide to use must be more carefully evaluated. The most immediate solution that could come up to our mind could be to develop a single shader that contains both the wet and the dry versions of our terrain, with a parameter handling the blending between the two. This is a simple solution, but it is far to be an ideal one. In fact, by doing something like this, we would at least double the complexity of our shader, even though at the end of the day we would be displaying just one of the versions most of the time. Since wetting a material practically consists in adding a water layer that modifies its PBR properties, we can think of achieving such result with some simple math. In this example, we will have to work on the material base color, roughness and normal. Let's start from this very simple shader that samples three textures and nothing more. What we have learned from our real-life experience is that dirt, when wet, becomes darker, more reflective and smoother. These three changes can be translated to lowering the base color and roughness values and blurring a little bit the material. The base color darkening can be achieved in several ways. My favorite is to square it. Since the values are lower than 1, the result will be darker, with the nice side effect of increasing the color saturation. After doing that, we can add a parameter to handle the intensity of our operation. For the roughness, we can simply identify which the water roughness value is and interpolate to that. Depending on the specific type of material you're working with, it isn't always appropriate to do this, but for this example we are fine. Earlier I was talking about blurring the material a bit. There are many ways of doing that, but for what we need, we can take advantage of a simple trick. Telling the GPU to sample an higher MIP level than needed through the MIP bias parameter. If you don't know what a texture MIP level is, you can follow my previous video about breaking texture repetition. Now we can add one more parameter that globally handles the effect we built. In this way, we are able to decide how wet this terrain is. Now that we have a somewhat satisfying wet version of our material, we can improve on it and work on the transition between the states too. First of all, I want to make the intermediate states more realistic. To do so, we'll introduce some procedural puddles, which will come handy to have a better wet material too. To generate said puddles, we'll need a height map. We'll use the height value to generate a mask that will tell us where the puddles form. To do so, we just have to add another parameter that will represent the water height and use it as a threshold. Now, every height value below the parameter will be white and considered a puddle, and every value above will be black and will remain untouched. We'll use this mask to flatten the normals and maxing out the other values transition. Before moving on, let's convert the mask from binary to a gradient. This gives us a smoother result and will come handy later. Now let's dive deeper in the situation where it's sunny after the rain, so you have the dry soil, but the puddles are still there. We can identify 4 different consecutive states of the ground that, combined together, will give us a realistic transition from dry to puddle. First, the ground humidity rises, so it becomes darker, so the base color lowers. Second, the humidity builds up and the ground starts to look visibly wet, so the roughness lowers. Third, the ground loses compactness due to the amount of water absorbed, so the texture gets slightly blurred. Fourth, the ground can't absorb the amount of water anymore, so the puddles form, so the normal flattens. As you may have noticed, we already have discussed all these cases. Now we just have to create different gradients to blend them in at different height values. We'll start by taking the puddles mask and multiplying it by the number of the states. Now we can separate the fractional part of every integer to create the masks we need. We can do that by subtracting the index of the mask we want to isolate and clumping the values. Now we have 4 different gradients that are one higher than the other. and we can use them independently for every PBR property modulation. Now that we have the system working, it's time to check if we have all the ranges working correctly. As you can see here, with our water level, we can make the whole terrain become a pond, but we can't return to the complete dry condition. This happens because our states are added one upon each other, so they are not reaching zero when the water level is. One way to fix this is to expand the water level range, to be from negative sum of the gradient ranges to 1. Since we want to keep the parameter in 0-1 range for usability and because the transition ranges may be changed, we are going to remap the water level range parametrically. In this case, we need to multiply the water level by the sum of the gradient ranges plus 1 and subtract that same number from the result. After all this work, we finally have a complete weather system on our material. To make everything more clear, we can rename some parameters to best fit their function. For example, the material wetness parameter can become a rain amount parameter, and the puddle's height parameter can become a max water height parameter, which will set the maximum height of the puddles. And the dynamic will be driven by another terrain wetness parameter, which will keep its full 0-1 range. This video was more of a practical application of the knowledge I shared in my previous videos than an explanation of a new concept. It was about a real world case scenario that hopefully has given you the opportunity of understanding how those concepts can be applied. There are many more of them, of course, which will be discussed in future videos.